Hello, everyone. Welcome to Unit 8. We're going to talk about the normal distribution in this unit. Probably one of the most vital parts of any statistics course is learning about the normal distribution. So let's start. We're going to learn what the empirical rule is. The empirical rule is also known as the, hold on, give me a second. Let me get this. There we go. Zoom in. The 68, 95, 99.7 rule. And that's because 68% of the data lie within one standard deviation, 95% of the data lie within two standard deviations, and the 99.7% of the data lie within three standard deviations. All right, so let's dig into this a little bit. Let's try and understand what we're talking about. So this is a normal distribution shape. Now, we've seen it maybe as like dot plots or histograms before. Just imagine, a dot plot that we've seen in the past. You guys have seen it where maybe the center is a bit taller and sort of, you know, tails off on the left and right. You've seen these dot plots before. They kind of make this overall curve shape to them. And when it makes a shape like that symmetrical shape, we have this a normal distribution is what we call this. So let's talk about the 68, 95, 99.7 rule and what 1, 2, and 3 standard deviations mean. So in the middle of the normal distribution, it'll come as no surprise. We have the mean, right? And then right around here or so, this would be one standard deviation. And then, a second standard deviation, and then a third standard deviation. So just some distance away. Whatever the standard deviation is, it's a measure of a distance from the mean, basically. Of course, you have on the left side the same distances, but the negative. So -1 standard deviation, -2 standard deviations, and then -3 standard deviations. All right, so let's get into the 68, 95, and 99.7 rule is. So again, you can kind of imagine there's a dot plot inside here if you want to, but for now, just look at the shape. So the 68, 95, 99.7 rule says this. 68% of all the data is within one standard deviation of the mean. So basically, imagine a dot plot. 68% of the points of the dot plot would be within this region here, from one standard deviation below to one standard deviation above the mean. So it's basically just talking about how spread out the data is. 68% of the data is within one standard deviation or this distance of the mean. Again, it measures how spread out it is. Now, 95, you can kind of see where this might be going. 95% of the data is within two. So from this part to this part of the distribution, 95% of the data lies within this region. So most of the data would be within this distance here. And then finally, we have 99.7, which will go all the way out to 3. Kind of out of room. Should have saved a little bit more space, but 99.7%, almost 100% of the data will be within 3 standard deviations. So only a very little bit of the data would possibly be out here on the outskirts beyond 3 standard deviations. All right, so this is our empirical rule. This is our normal distribution, right? 68, 95, 99%. These percentages do not change. They are true for standard deviations. It's kind of tied together. The way we measure how far one standard deviation is based on this information as well. So 68% of the data will always lie within one standard deviation. They coincide with each other. Same thing, of course, with 95% with 2 standard deviations, and 99.7 with 3. So a standard deviation is measured based on some of that information. So the empirical rule gives us approximations, which are great to use when estimating area under normal curves. However, we will also learn methods to be more precise. The weights of adorable fluffy kittens are normally distributed with a mean of 3.6 pounds and a standard deviation of 0.4 pounds? Answer the following questions using the empirical rule. Before I get into these questions, I want to outline one more key detail about the empirical rule. So let's go back to the second chart over here and kind of make the same but slightly different version of this graph. So again, mean in the middle, 1 standard deviation, 2 standard deviations, 3 standard deviations. Same thing over here, negative 1 standard deviation, negative 2 standard deviations, negative 3 standard deviations. All right. And what I want to point out, see if I can, how well I can do this. It's kind of hard to draw straight lines sometimes. Just to break this up a little bit, if you kind of section this off, right? 68 and 68 in total, this would mean that there's 34% on either side, right? Hopefully that makes sense, right? 34% here, 34% here, right? That's what equates to 68, right? So kind of 34% on the left, 34% on the right, just to kind of help us in the future. You're going to see we're going to need kind of this information. If we look at 2 standard deviations, it goes to 95, right? Now 95 minus 68, if you kind of see what's left over here. So if we have 95, but we take out 68 from it, we have, I believe 27, no? 90, 70, 20, yeah, 27. So we have 27% to distribute to either side here. So because we're going to split it in half of 27 is 13.5. So that means 13.5% will be on this side, 13.5% will be on this side. And so now, again, if you added all 4 of these together, this would add up to 95%. 13.5, 34, 34, and 13.5 should total to 95%. But now we need to get to 99.7. See, how much is this little region here? Well, take the difference. 99.7 minus 95 is 4.7. So we have 4.7 that needs to go split between these two regions. So if we cut 4.7 in half, that'll give us 2.35. So that means each of these little regions here is worth 2.35%. And then finally, because that has to add up to 100, right? The only thing remaining, because this is 99.7, the only thing remaining would be 0.3. 0.3 is split to either side. So again, if we cut 0.3, the remaining amount in half, then we'll have 0.15% here and 0.15% here. So now it's 100% of the data all accounted for. So this will help us, these distinguished regions, because we're going to have to find certain areas on their certain parts of the curve. So you'll see, we'll get to it. All right, so what percent of kittens weigh less than 2.8 pounds? Before I can answer this, I'm going to have to draw out my normal distribution. So let's have some practice actually, I guess drawing one out for the first time. So we know it's a normal distribution, right? So let's go ahead and make our graph of this. Just kind of a sketch. It's not going to be beautiful, but it's going to get the job done. Now, notice it says the mean weight is 3.6. So of course we know that that's going to be the center of this distribution. And then standard deviation is 0.4. So if the standard deviation is measured at 0.4, then one standard deviation, 0.4 higher, will be at 4.0, correct? Because it's 0.4, right? We're adding 0.4. That's one standard deviation away. A second one would be at 4.4. And then the third one will be at 4.8, right? Because standard deviation is 0.4 pounds. So each standard deviation increases by 0.4. Of course, we need to go backwards too. So if we go backwards, then we'll subtract 0.4. This will be at 3.2. This would be at 2.8. And then finally at 2.4. All right. It's not the most perfect to scale graph, but it gets the job done. So now it's asking what percent of kittens weigh less than 2.8. So you're going to notice, so let's label these, right? Hold on a second. You have the mean in the middle. We have 1 standard deviation, 2 standard deviations, 3 standard deviations, and then -1 standard deviation, -2 standard deviations, -3 standard deviations. You're going to notice that 2.8 is right here at -2 standard deviations. And we're looking for the percent that weigh less than 2.8. So that's this area here, everything less than 2.8. So we want to know what this percentage is. Now, go back to the graph that I made recently. That coincides, if you're paying attention here, that coincides with this region right here, right? Everything below the -2 standard deviation. So it's not 2.35 because it's also including this part here, this 0.15%, because it's not just between -3 and -2, it's all that's less than 2 standard deviations. So 2.35 combined with 0.15, which means this region here altogether adds up to 2.5%. So that region amounts to 2.5%. So our answer, 2.5% of kittens weigh less than 2.8 pounds, right? There you have it. So nice. Number 2, what value corresponds to a 97.5th percentile of kitten weights? Okay. So percentiles will count upwards. So let's see how we can annotate this real fast. Let's go, what color haven't I really used yet? I guess we can use something boring, like this brown or something. So percentiles. So they kind of add up, right? So like the mean here is going to be the 50th percentile, right? All the way down here would be the 0, right? All the way up here would be 100. So if you go to 0.15%, this will be, we're going to add these up as we go to the left. So this will be the 0.1, oops, hold on, gotta put it on. 0.15 percentile at the 3rd standard deviation. This will be the 2.5th percentile, right? We're kind of adding them up, right? We're, like I said, we're adding up as we go. Let me erase the yellow here because we don't need that anymore. Can I? There we go. Adding 13.5% now. This is means that first standard deviation that's at the 16th percentile. Right? We add 34 to 16, we're going to get to the 50th percentile. We add 34 to the 50th, we're going to get to, here would be the 84th percentile. So again, if you're curious, what am I doing? I'm simply adding these percentages up as we go. We're starting at 0. This gets us to 0.15. Then we add these two, we get a 2.5. And we're adding these 3. That gets us to 16%. We add all of these 4. That gets us to 50. Then we're adding all of these 5. And that gets us to 84. And so on. So we're going to keep adding. So we're going to add 13.5 to this. And that's going to put us at 97.5th percentile. We add 2.35. This will put us all the way at the 99 point. See, add 0.35, 0.85 percentile. And then all the way, if you can go down to infinity, you'd be at the 100th percentile. But you'd have to go all the way to infinity to get to that. So, but that's our percentile scale. Maybe that'll help us. So it's asking about the 97.5th percentile, which, as you can see, is going to correspond with the 2nd standard deviation. And then this is always true. Like these numbers never going to change, right? But as you can see, the 2nd standard deviation in the kitten case is at 4.4. So that means 4.4 is that 97.5th percentile. I'm just going to redraw the graph here just to label it. 4.4 pounds. All right. Nice. So yeah, hopefully we get used to it. Basically, just all the answers are going to be on this chart pretty much. So as long as you can, memorize this or at least just have it handy, it's going to be our resource answering pretty much everything. So let's look at a couple more examples. All right. Lifespans of lions in a particular zoo are normally distributed. The average lion lives 12.5 years and the standard deviation is 2.4. Use the empirical rule, estimate the probability of a lion living between 5.3 and 10.1 years. So you can't really do this without drawing the graph. So let's draw the graph. We probably don't really need to draw the curve part, but I guess it doesn't hurt because we really just need a number line, right? The average is 12.5, so we have 12.5 in the middle. And then each standard deviation is, how much did it say? 2.4. So we have to add 2.4. I don't want to mess this up, so I'm just going to grab my calculator. All right, so 12.5 plus 2.4, we have 14.9. We're going to add it again. We have 17.3. And then we're going to add it again. We have 19.7. Now we need to subtract, right? 12.5 minus 2.4. So this will be 10.1. Do it again. Minus 2.4, we get 7.7. Then one more time, we get 5.3. All right. So there's a number line. So remember, it said between 5.3 and 10.1. So 5.3 is here, of course. The 10.1 is here. So I'm looking to see how much percent this adds up to. So if you're keeping track, then you'll notice that this is between the negative third standard deviation and the negative first standard deviation, right? From the negative third to negative 1. So if we go back to our chart, that helps us out. That's going to be this region here, right? That's from the negative third standard deviation to the negative first standard deviation. So right in here, we have to add these two together. So it's 2.35 plus 13.5, which is 15.85. So our answer is that this would add up to 13.85. Right, let me be more specific, right? So you guys can see. So it's 2.35 and it's 13.5, which adds together to make 15.85%, obviously. All right. So again, it helps. All you got to do, really draw the number, right? Find which region it is, and then go to that little chart here to help, see your percentages a little bit better and add them all up. Okay, it's hard to erase the highlight sometimes. Come on, don't be like this. All right. Oh my gosh, the highlighter, the eraser is just difficult sometimes. All right, just leave it alone. All right, so we're gonna another question. Lifespan of lions, particularly zoo, normally distributed with average of 10 years. Standard deviation is 1.4. So let's make our number line for this. So I'm gonna make it a little longer so it's easier to spread out a bit. So mean is 10 years, right? 10 years. Just don't worry about that. Curve doesn't have to be perfect. All right, standard deviation is 1.4. So we got 10 plus 1.4, which is 11.4. That's one standard deviation. Plus 1.4 again, we had 12.8, which is 2 standard deviations. And then one more time, we got 14.2, just 3 standard deviations. We go backwards as well, 1, 2, 3. So we have 10 minus 1.4, which is 8.6 at -1 standard deviations, 7.2 at -2 standard deviations, and 5.8 at -3 standard deviations. All right, so the question is, estimate the probability of a line living longer than 7.2. So longer than 7.2, that's from here and it's upwards, right? It's all of this. Everything longer than 7.2. So everything here all the way down to infinity, basically, right? All right. Now, there's kind of 2 ways you could do this, maybe. You can add up all of these, right, from -2 upwards, or just take 100% and subtract this region, right? That might be easier, actually. So this region here, remember, this was 0.15, and this is 2.35. So let's just take 100 and minus those, right? And essentially this will come out to a total of I think 99.7. Yeah, or not 97.5, sorry, 97.5. So our answer 97.5%. So that's one way of doing it, is taking 100% and subtracting this amount, because this is obviously not counted. Or, like I said, you can just count, instead of just subtracting these two, you can just add up all of these. So from 13.5 to 34 and 34 to 13.5 to 2.35 to 0.15. You can add up all of those if you want, or just take 100 minus these two, which is what I did. All right, one more. We have lifespan of tigers in a zoo. Okay, cool. Average tiger lifespan is 22.4. So let's draw this out again. So 22.4 is our average. So that'll be in the middle. And standard deviation is 2.7. So we have 22.4 plus 2.7. We have 25.1. Plus 2.7, we have 27.8. And then we have 30.5. Then let's subtract as well. So 22.4 minus 2.7, which is 19.7. Minus 2.7 again, we're at 17. And then minus 2.7 again, we're at 14.3. So again, that's the mean. 1 standard deviation, 2 standard deviations, 3 standard deviations, -1 standard deviations, -2 standard deviations, -3 standard deviations. So we're asked to find probability of a tiger living less than 14.3. So 14.3 is here and it's less than, so it's just this tiny little bit here. So if you remember from our chart, this is 0.15%. And that's all there was, because there's nothing else add up. That's that region. It's less than 3 standard deviations, which, as you can see from up here, less than 3 standard deviations is only that 0.15. I need to make sure I fill this in again. I must have erased it by accident up there earlier. All right. So, yeah, that's the only region here that we're looking for, living less than 14.3. Yep, definitely 0.15%. All right, that's going to do it. This is a good start to our empirical rule. If you got any questions, let me know, and I'll see you guys in 8.2. Bye for now.